joined so far. So attendance is poor, rather. Okay, but let me start. Have to start the lecture today, and I shall have to continue it. It will be better if you join in what I should say. Obviously, more number of students should join, should attend the classes. Otherwise, these type of courses, arranging classes online will be of no meaning. What I can do, I can send you the PPT or PDF, send you the content, you can read. If you feel that that is good, I can do that, no problem. But if you feel that classes are to be held, classes are to be attended, then a more or a greater participation is desired. Okay. All right. So let us start today's content. Shall be recording the session so that later on I may mail these lectures to you if it is needed at all. Can you see the screen? Is it visible?
Yes, sir.
Okay. So in our last class, we have basically discussed the what should we should be actually studying in this course, and we have discussed why frequency control is necessary, why voltage control is necessary, what is the main reason for frequency variation, what are the main reason for voltage variation, and how frequency and voltage controls may be actually implemented in power system. These things were discussed. We have some other things to be discussed. This basically is due to the stability portion. That means the integrated operation of power system. So we shall be first discussing with frequency control and voltage control. Then we shall be discussing regarding the stability, because otherwise it will not be very easy to actually understand that portion. So that's why we shall be mentioning that part later on. Now you see that frequency control, already we have mentioned that it has to be done from the power station. Okay, it has to be, let me check whether the recording is there. It has, yes, recording is there. So frequency performed from power stations, because for frequency variation, what is responsible is the unbalance between the active power generation and the active power demand. So whenever there is an increase in the frequency, we shall have to arrange for the reduction in the power generation. If there is a reduction in the frequency, we shall have to attempt to increase the power generation. And that also can be done from the power stations only. Therefore, frequency control is possible from power station only, from central locations only, and power stations are those locations. But voltage control, as we have mentioned, it is possible from generating station as well as from the substation. Okay, substation means transmission and distribution substations, where you can actually install reactive power sources. Why we are mentioning about reactive power sources in respect of voltage control? Because we have seen that for voltage variation, it is the reactive power unbalance between the load and the generation that is responsible for the voltage variation. So that reactive power generation may be controlled from power stations through synchronous generators. They may be controlled, reactive power generation may also be controlled from substation through the installation of static bar compensators, through the installation of shunt capacitors, switch shunt capacitor basically, and also through the installation of the so-called STATCOM. So all these devices are available. Therefore, you can say that reactive power control or voltage control is rather distributed, and frequency control is basically a centralized control. Since both frequency and voltage may be controlled using generators, synchronous generator, we shall be now discussing about synchronous generator first, and then we shall discuss how frequency control is possible through synchronous generator and how voltage control is possible through synchronous generators. Okay, so let us today start with synchronous generators. Already we have mentioned that most of the generators in power system are synchronous. At least 80% of total generations almost in any power system is from synchronous generators, because at least 80% of power in most of the power station is coming from either thermal power stations or hydroelectric power stations. Okay, these are the conventional power systems. And the remaining 20%, on an average rather, it is on remaining 20% is coming from other sources like induction generators, like battery, like you can see the devices. Okay, so let us start with synchronous generator. Synchronous generator, you know that they actually run at synchronous speed. That means they are run at a constant frequency. They should maintain constant frequency operation. So constant frequency means there is a relation between the number of poles, speed of the rotation, and uh, number of poles. So you see that whenever you are deciding upon the frequency of power transmission, that is 50 Hz in our case, and when the number of poles of a generator is already decided, because generator, whenever you are actually manufactured a generator, you have manufactured it for a certain number of poles. So speed is constant, speed is known. What is the synchronous speed for a particular generator, that is known, and the generators must run at that speed so as to generate synchronous frequency power. Okay. Now, in the discussion of synchronous generators, what we shall do, those synchronous generators will be discussed in other courses also, like a machine course. But the approach we shall follow here while discussing the synchronous generator in a power system course will be somewhat different. In what way it will be different? We shall be assuming that our synchronous generator is connected to the power system, and power system always is a very large system, having a very large power capacity. In our previous conference, I have mentioned that what is the total generating capacity, total installed capacity in our power system, in Indian power system, that is around 370 gigawatt. 370 gigawatt means 370,000 thousand megawatt. Okay. Now, what may be the capacity of a synchronous generator? Can you guess the capacity of a synchronous generator? Generally, what are the capacities? It is not the exact figure I want, the approximate figure. Can anybody tell me what is the capacity of a synchronous generator? What may be the capacity? Anybody? What is the capacity? Power capacity means megawatt capacity. Okay. What is the power capacity of a synchronous generator? What
Sir,
may be?
500.
500 megawatt. Maybe somewhat less, maybe sometimes more than 500 megawatt. That means synchronous generators maybe around 500 megawatt, maybe 300 megawatt, maybe 800 megawatt, maybe even 1000 megawatt. Let us assume that we are having a synchronous generator of large capacity, say 1000 megawatt. So, with respect to that generator, what is the total capacity of our system? It is 370 gigawatt. That means 370,000 megawatt. So you see that if you see the capacity of the synchronous generator with respect to the total capacity of the system, it is really very small. We have mentioned about a very large generator of the order of 1000 megawatts. Sometimes these generators may be of smaller size, 200 megawatt, 300 megawatt, 400 megawatt. So what is the capacity of a single generator? That is very small with respect to the capacity of the total system. so small that what we may assume that even if that generator is delivering power to the power system, whatever may be the variation of power delivered, there will be some impact on the system, but that impact will not be very large. It will be a small impact because of the capacity or because of the relative small capacity of the generator. Impact created by the variation of generation of the generator on the performance of the total power system is rather very insignificant. That much we can uh, or we shall be assuming. Why we shall be assuming in this way? Because the capacity of the generator is very small with respect to the total capacity of the power system. Obviously, there will be some impact. There will be some variation in system parameter if we vary the power output of our generator. But to keep things simple, what we shall be assuming now that as if there will not be any impact on the performance of the power system if we vary the power output of our generator. So we shall be assuming that we are connecting our generator to a power system, okay, which is very, very large. And the total power system, we may assume that the point where we are connecting our generator may be considered to be a bus or to be a bus bar, where we can say that the equivalent capacity of the total power system is represented, okay, maybe by a single generator. So what we should do, as if we may assume that total power system capacity or total power system may be represented by a single generator connected at the terminal of the generator, okay, that we are connecting to power system. And what will be the capacity of that single generator representing the total capacity of the power system? That will be very, very large with respect to the generator we are connecting to power system. Okay. So this bus where a very, very large size generator is connected, so large that we may assume that that is of infinite capacity. So we shall assume that as if we are connecting our generator to a bus that may be termed as infinite bus. And this basically is a concept in power system. Obviously, such bus will not exist in power system. Okay, but we shall assume that as if we are connecting our generator to power system, and that system is such that it is of infinite capacity. So we shall say that our generator is being connected to a bus which may be termed as the infinite bus. Okay, and we shall assume something as the property of that infinite bus. What are those property? We shall assume that that bus is having the capability of maintaining constant voltage. That means the point where or the bus where we are connecting our generator, as if voltage of that point is not changing. Whatever may be the change in the load of the system, that the voltage of that point where the generator is being connected will not change. That means we shall assume that that infinite bus is having constant voltage. Or in other words, we can say that we shall assume that our power system is as if behaving as a constant voltage source. Okay, it is behaving as a constant voltage source so that it is maintaining constant voltage at its terminal. And what is the terminal? Terminal is that point where we are also connecting our generator. Okay, so that bus where we are connecting our generator will be termed as an infinite bus. Okay, what are the other properties of this infinite bus? As we have mentioned, it will be having constant voltage. We are assuming that that bus will be maintaining constant voltage so that we can say that as if our power system is behaving as a constant voltage source. If that bus is behaving as a constant voltage source, what will be the impedance of that bus? Do you know the property of constant voltage source or an ideal voltage source? What is the property of an ideal voltage source? Impedance is zero. That means impedance connected in series with the voltage source is zero. So in our case also, our infinite bus will have zero internal impedance. That means as if our power system is represented by a voltage source with series impedance, where the series impedance is having a 0 ohm impedance. Okay. Then again we shall assume that our power system, that means that bus, infinite bus, it is having constant frequency. That means how it can maintain constant frequency? Whatever may be the power drawn from this bus, whatever may be the power injected to that bus, okay, the frequency of the system, that means the frequency of the bus will remain constant. That means the system will behave as a constant frequency source. All right. Now, can you tell me what will be the other property of a bus that can maintain constant frequency? Basically, what we are doing, we are actually representing the total system by a single generator, and that generator is maintaining constant frequency. If that generator is maintaining constant frequency, what should be the property of that system such that it can maintain constant frequency irrespective of the variation in the power input or power output from the bus? বুঝতে পেরেছি? যদি কোনো একটা বাস অথবা কোনো একটা জেনারেটর রাদার কনস্ট্যান্ট ফ্রিকোয়েন্সি সবসময় মেনটেন করে, তাহলে তার কি প্রপার্টি থাকলে দ্যাট ক্যান মেনটেন কনস্ট্যান্ট ফ্রিকোয়েন্সি অপারেশন irrespective of any variation in load or generation? বলো। When a busbar, or why we are talking about busbar? Because we are connecting our generator to busbar, and at that busbar total power system is represented by a single generator connected at that bus. So what will be the property of that generator that is maintaining constant frequency operation irrespective of any variation in the load drawn from it or power injected to it? Synchronous speed, that means it will maintain constant frequency. Okay, but কি থাকলে পরে constant frequency, মানে constant frequency মানে কি, সেই জেনারেটরের তুমি you are not, you cannot change the speed of the generator. অবশ্যই constant frequency maintain করা মানে certainly the generator is generating that frequency, it is generating a voltage whose frequency is constant. তার মানে এটা কখন সম্ভব যে it is maintaining constant frequency operation? Okay, that means its speed cannot be changed very easily. That is the implication. So, what will be the basic nature of a generator whose speed cannot be constant very easily, cannot be changed very easily? তুমি এর স্পিডটাকে ভ্যারি করতে পারতো না, ভ্যারি করাটা খুব ডিফিকাল্ট। দিস ইজ দ্য বেসিক কনসেপ্ট। বলো তখন সেটা সম্ভব যে স্পিডটা ভ্যারি করানোই যাচ্ছে না প্রায়?
যখন ইনপুটটা কনস্ট্যান্ট থাকবে টারবাইনে।
ইনপুটটা কনস্ট্যান্ট, আমরা তো বললাম ইনপুটটা ভ্যারি করতে পারে। কেন? এই যে বললাম লোড চেঞ্জ করতে পারে, জেনারেশন চেঞ্জ করতে পারে, অর্থাৎ যেই জেনারেটরটা আমি কানেক্ট করব টু দ্যাট বাস, দ্যাট জেনারেটর মে ডেলিভার এ স্মল অ্যামাউন্ট অফ পাওয়ার, may deliver a large amount of power. Load connected at this bus may draw a large amount of power, may draw a small amount of power. Whatever may be the condition, that bus will maintain constant frequency. Means the voltage generated there, it is basically that representative generator. That generator is maintaining constant frequency operation. When it is possible, when the rotor of that generator is very very heavy, okay, the rotor mass is huge, তার মানে কি রোটরটা অনেকটাই ভারী, আর একটা rotor mass of the rotor is very heavy. That means rotor is having infinite inertia. Then only for changing the speed of the generator, it will be very very difficult. Very very large force has to be applied if you want to change the speed of the generator. That force usually we shall not be in a position to apply, so cannot change frequency. That means when we talk that, when we say that the frequency will be constant, means the inertia of the generator is infinite. Okay, that means the infinite bus, this concept, we are assuming that our generator is connected to an infinite bus. So what are the basic properties of an infinite bus? It is having constant voltage operation, means its internal impedance is zero. It can maintain constant volt frequency, means it will have infinite inertia. Because infinite inertia means obviously rotor mass is very, very large. And then only if the rotor mass is very large, obviously changing the speed of that mass, because this is a rotating body, will be very, very difficult. You cannot change the speed of that mass unless you can change it, you can apply a very, very large force. So as if we are not capable of applying that force. That's why the frequency is remaining constant. So we shall be starting our discussion with this assumption. So what we are doing, we are assuming the presence of an infinite bus. In practice, this type of buses will never be present. Okay, এরকম বাস হয় না, হবে না, but what we are assuming that this bus is present, or we are connecting our generator to such a bus because we want to start our analysis, start our study by assuming that our system is actually having this property, because in that case we can actually focus our attention on the performance of the generator. We shall be assuming that something are constant in the power system. Then what we can do, by changing some other thing, we can see what is the impact of those variations on the performance of the generator that we are connecting to the power system. So for that, what we shall have to do, we shall have to assume that something in the power system will remain always constant, and then we can focus our attention to the performance of the generator that is being connected to the power system. So this is why we are assuming that we shall be connecting our generator to infinite bus. Okay, is it clear why we are assuming that a bus exists whose property will be like this? Because of this thing, we are assuming that there is a bus, or the bus where we are connecting our generator is basically an infinite bus. In practice, what is an infinite bus? Basically a bus where the capacity is very, very large. Okay, how much large? With respect to the generator that we are connecting to the power system, that the total capacity of the power system should be very, very large. Then only you can say that that power system will be behaving as an infinite bus. That means variation of frequency and voltage of that power system will be very small, because this generator is having a very small capacity, so it will have very little ability to change the voltage and frequency of the power system. So with this assumption, we shall start our analysis. Okay, now let us then start to see what are the different types of generators. Okay, because we shall be starting the performance of synchronous generator first. So what are the two types of generator? Generators are of two types. What are the two types? One is the cylindrical rotor type generator, salient pole type generator. Okay, salient pole and cylindrical pole type generator. So cylindrical rotor type means they are having uniform air gap. Perhaps you know all these things. Cylindrical means they are cylinder in a cylinder. Obviously, you can say basically we are talking about the generator. There is a stator winding, there is a rotor winding. Okay, rotor winding will be rotating inside the stator winding. So between the stator and rotor, there is an air gap, and their air gap has uniform width. Okay, so if this happens. This is possible if the rotor is having a cylindrical structure. Okay, such that its diameter is not varying; it is constant. Okay, so this is the cylindrical rotor type generator. So what are the properties of the cylindrical rotor type generator? Generally, these generators are having small diameter. Why small diameter is small? I shall explain. But I shall want to know from you first. They will have long rotor, they will have small number of poles, and their speed is high. Okay, and generally These generators are connected in thermal power stations. So in thermal power stations, what are the turbines? Turbines are the steam turbines. Steam turbines actually uh, operate efficiently. Steam turbines, they can operate efficiently at very high speed. So their operation is efficient at a very high speed. Since we shall be using steam turbine at thermal power station, so our generator also should rotate at a very high speed. When the generator can rotate at a very high speed, when its construction is very rugged, if the rotor is cylindrical type, is cylindrical in structure, then its ruggedness is it has a very rugged structure. Okay, because it can rotate at a very high speed. That means its rotor will not be deformed. There will not be any problem to the structure of the rotor if it rotates at a very high speed. When this is possible, when the cylindrical when the rotor itself is very rugged. Okay, so cylindrical rotor type machine is having this property. Okay, since they are rotating at a very high speed, obviously their number of poles need not be very large. So if the number of poles need not be very large, so we shall have to use a small number of poles. So to accommodate small number of poles, we need not have to keep the diameter of the rotor very large. So diameter will be rather small. That's why cylindrical rotor type machines will have small diameter. Okay, and they have small number of poles already I mentioned. Because why small number of poles? Because F equal to Pn by 2, you know. Okay, if the number of if the speed is high, number of poles may be less. That's why number of poles are less. If the number of poles are small, then obviously the diameter can be small. Okay, and since their diameter is small, their rotor will be rather heavy, large length. Okay, so rotor are long rotor, and diameter is small, speed is high, and generally this type of machines, this type of synchronous generators are used in thermal power stations. The another type is the salient pole type. Salient poles are also called the projected pole. That means poles are salient. In cylindrical rotors, poles are not salient. Okay, in salient pole machines, poles are salient, poles are projected pole. Okay, so projected pole machines cannot have very rugged structure. Okay, so they will be able to, or they should be rotated at a very low speed. And since they will be rotating efficiently, or they can be rotated at a very low speed rather, they are more suitable. They are suitable for hydroelectric power. Okay, then steam turbine, water turbine, you know that they can be rotated, they rotate or they operate efficiently at low speed. So this type of generators, in salient pole generators, they are used in hydroelectric power stations. Okay, and since the speed is low, obviously for generating the same required frequency, your number of poles has to be more. So the diameter of this type of machines has to be large. Okay, so they have large diameter. And since they are large diameter, rotor is short, low speed already I have mentioned, and this projected move means, okay, at the pole location there will be some projection. Okay, so they are having unequal air gap, having unequal air gap. So cylindrical rotor machines are having equal air gap everywhere in the diameter, and salient pole machines are having unequal air gap. Since they are having unequal air gap, their analysis is rather complicated. Why it is complicated? Because of the presence of unequal air gap, you have to represent this type of generators with the help of two reactances. One reactance is along the pole axis, and another reactance along the quadrature axis. That means 90-degree with the pole axis. Why? Because the reluctances are different along the pole axis and along the quadrature axis. Since they are different, so we have to represent them using two reactances. Since the reluctances are different, flux will be different. As a result, reactances also will be different. But in case of cylindrical rotor type machine, since they are having uniform air gap, that means since they are having uniform reluctance everywhere, they can be represented by a single reactance. So naturally, a machine that you can represent with the help of a single reactance will be simpler to analyze with respect to another machine that has to be represented by two reactances. Okay, that's why analysis of cylindrical rotor synchronous machine, cylindrical rotor type synchronous generator rather, will be much easier. And to keep our analysis simple, we shall henceforth assume that our generators are all cylindrical rotor type. Okay, why you shall be assuming this? Because we want to keep our analysis simple. But later on, we shall show that the same analysis will be valid if we apply this on salient pole machines as well. So that also we shall show. That means we shall be considering the presence of cylindrical rotor generators only in power system, because if the rotors are cylindrical, analysis will be simple, and we shall be keeping our analysis simple. That's why we are assuming that all generators are cylindrical rotor type. But at the same time, we shall also show how this same analysis may be extended to analyze the performance of salient pole generators as well. Okay. Now, to start with the analysis of the generator, we shall have to start with the phasor diagram. Okay, phasor diagram of the salient of the cylindrical rotor type generator. And from phasor diagram, we shall be developing the equivalent circuit. And from equivalent circuit, we shall be developing active and reactive power equation. So you see, we are starting with phasor diagram, developing equivalent circuit with a purpose to write the active and reactive power equation. Why we are doing so? We are not going to other type of analysis, other type of performance analysis of synchronous generators, because we are observing the synchronous generators when it is connected to power system. We shall be studying the performance, studying the behavior of synchronous generator when it will be connected to power system. That's why this will be our actually method of analysis, method of study. Okay. So let us start the drawing the phasor diagram of synchronous generator. Synchronous generators, whether it is cylindrical type or salient pole type, obviously it has two winding. One is the stator winding, another is the rotor winding. Okay, stator windings are on the armatures are on the stator winding, and rotor winding is having the field. Okay, so DC field is on the rotor and armature is on the stator. Three-phase armature winding on the stator and rotor winding is on the rotor. Now the question is, why the DC field winding is kept on the rotor? Why it is not kept on the stator? Do you know this? Any idea? Why it is so that generators are having field winding on the rotor, not the armature winding on the rotor. Okay. Follow?
Sir, in case of DC field winding, if we keep it the field winding in armature, then if an armature in the rotor, then if when we collect the output, then we should give a slip ring arrangement, so there will be more loss. But in case of field winding in the rotor, but armature in the stator, there will be no need of slip ring because armature is static. So we directly take output voltage from the armature.
But will it not be needed to supply power to the field winding? Because field winding you have to supply DC, so some DC supply is needed. It has to be connected to rotor winding also.
Sir, but since there is a AC winding which has to go into the armature, if we put the AC winding on the rotor, then we will have to put 3 wires before the 3 phases. However, if this is a DC winding, only 2 wires are required. So that is one advantage. Then, sir, it is easier to cool if the armature is on the stator. Cooling is easier. There are various other reasons, sir. There are two, three other
The
reasons.
And
armature winding is more heavy than the DC field winding, because DC field winding rating is very less than the armature winding.
okay,
So
why it will be more heavy? Because actually the armature power capacity is much larger than the field power capacity.
yes,
Okay, what will be the power capacity of the field winding? It is very small because you will be supplying power to the field winding only. So, what will be the purpose of supplying power to the field winding? Only to create the magnetic field. On that magnetic field, the armature will rotate and voltage will be induced. So, basic purpose of supplying power to the field winding is to generate the magnetic field. To generate the magnetic field, we need not have to supply a large power to the field winding. A small amount of power has to be supplied. So when you are supplying a small amount of power, obviously current related with that power also will be small. That means you will be supplying a low current rather to the field winding. But if you connect the, if you install, or if you install the armature winding on the rotor, then since the power capacity is more, then drawing current, drawing large current from the rotor winding will be much more difficult. Okay, you are supplying power to a rotating winding. Obviously, you are doing this because the field winding is also having some power supply requirement. But see that uh, that power is rather a small amount of power. So it will involve low current. So supplying low current will be much easier than drawing large current from the rotating winding. Okay, so that is the reason. All right. So now you see that we are supplying DC current to the field winding, and field winding is on the rotor. So if the rotor is having a number of poles, and say this is representing the axis of the rotor. Okay, rotor axis and rotor field axis. Okay, so as if this is the field axis. So where is the winding? The windings are on the actually rotor core, rotor pole core. Okay, so now assume that if this is the rotor pole core. So if is it visible? I think say this pen is showing you the pole core. Okay, and this will be the nature of the pole winding like this. So I am actually holding the rotor winding like this, and these are the winding sense of the winding. So if it is the sense of the winding, current is flowing in this way. What will be the direction of the flux? Direction of the flux will be represented by the thumb. Okay, direction of flux will be represented by the thumb. That means flux will be along the axis of the pole. Am I clear? Flux will be along the axis of the pole. That axis we shall be henceforth referring as the D axis or rotor axis, direct axis of the rotor, or which is pole axis of the rotor. Okay. So basically, when you are supplying current to the field winding, field flux will be produced, and this will be the direction of the field flux, and this direction is along the axis of the rotor pole, or we call it the D axis of the rotor. And 90-degree with the direct axis is the quadrature axis. That means 90-degree away from the pole axis is called the quadrature axis. So field winding is rotating with the rotor. Okay, and the field current, that is DC current. So a steady current is flowing in the field winding. A magnetic field is created because of that current. Okay, and the field winding is rotating at synchronous speed because rotor is rotating at synchronous speed, and stator windings are on the armature windings are on the stator. So EMF will be induced because of this rotating magnetic field. Okay, because the magnetic field is rotating here with respect to the stator winding. So on the stator winding or on the armature winding, the EMF will be induced. So what will the phase relation between the field flux and the EMF induced on the armature winding, that will be 90-degree lagging. That means the generated voltage EF will be 90-degree with the field flux. Okay, that means it will be lagging 90-degree with respect to the field flux, or it will be lagging 90-degree with respect to the direct axis of the rotor. Or we can say that generated voltage will be along the quadrature axis of the rotor. Why? Because field flux is along the direct axis, 90-degree with this is the quadrature axis of the rotor. It is lagging by 90-degree. So generated voltage will be along the quadrature axis of the rotor. Is it clear? What I have said here, it is clear or not? Could you understand this? We shall be now drawing the Phasor diagram. So how we are drawing the Phasor diagram? I am explaining that. So could you understand why this will be the direction of the field flux? It will be along the axis of the rotor, and why EMF generated voltage will be along the quadrature axis of the rotor. Is it clear or not?
Yes, sir.
Yes. Now assume that our generator is delivering some current. It is delivering current to a load. What is the basic nature of a load? Our system is a load থাকে, average loads are inductive in nature. Okay, they are inductive in nature. That means voltage and current. What is the phase relation for an inductive current, inductive load? The current to lag the voltage by 90 degree. Current to lag the voltage by some angle, by the power factor angle. So let us assume that this IA is representing the direction of the load current or phase of the load current. Okay. So because of IA, that means this is a stator winding or armature winding is carrying this current, it is delivering this current to the load. Now, when this current is flowing to the armature winding, a flux will be created due to this armature winding current. Okay, that flux we call the armature reaction flux. Okay, because of the armature current, a flux is created. Dash flux will interact with the field flux. That's why this flux we call the armature reaction flux. That means the armature current generates a flux, and since it will be interacting, it will be either distorting the field flux, it will be either modifying the field flux. That's why since it is creating a reaction with the field flux. That's why it is called the armature reaction flux. So what will be the direction of the armature reaction flux? It will be in parallel with the armature current, because this is the armature current. Armature reaction flux is represented by phi A. It is see that in the same direction as the armature current, because there is no saturation. We are assuming. That means flux and current, they are linear, having linear relations. Since they are having linear relation, if this is the armature current direction or the phase of the armature current, direction means in this case phase. Since this is the phase of the armature current, phase of the armature flux will be phi A like this. They are same phase. Okay, same direction. So if this is the field flux, this is the armature flux, the resultant of these two is the resultant flux phi R. So as if this is the resultant flux phi R, and because of this resultant flux, you will see that we shall have the resultant voltage. That means generated voltage, then some other voltage or representing some voltage drop because of armature flux. Okay, and finally this is the resultant flux. Because of this resultant flux, this is the resultant voltage or the terminal voltage Vt. Okay. Now, what is the relation between this resultant voltage or terminal voltage Vt and the generated voltage EF? This is the relation, that this voltage drop. Difference is this voltage drop. So Vt plus this drop is equal to EF, or EF minus this drop is Vt. Okay. What is this drop? This drop is occurring in the reactance of the armature, because this drop is due to the armature reaction flux. So this drop is occurring in the reactance of the armature. We are assuming here that our machine or generator is having negligible resistance with respect to its inductive reactance. Okay, obviously generators are actually designed in such a way that their loss is very small. So we can assume that this generator is having negligible resistance with respect to the inductive reactance. So that's why we are neglecting the role of resistance in this case. So if we neglect the role of resistance, the total drop will be due to the reactance only. Which reactance? This is the armature reaction reactance. Okay. So therefore, this is Vt, this is J times Ia XA. XA is the, or J times Ia XS rather. XS is the synchronous reactance of the machine. Ia is the armature current. It is JIA because this will be 90° with the current. Why 90° with the current? Because it is inductance, inductive reactance. Drop is in the inductive reactance. So because of the inductive reactance drop and current, there is a phase relation of 90°. That's why this is the direction of the drop. So Vt plus JIA XS is equal to EF. Phasor diagram of synchronous generators that we are discussing here. So phi f is the field flux, phi r is the resultant flux, Ia, this is the armature current, synchronous reactance is XS. What is synchronous reactance? Reactance offered by the generator when it is operating at steady state. That means when it is rotating at synchronous speed, then it is operating at steady state. Then the reactance is the synchronous reactance. Basically, this synchronous reactance is a combination of the armature reaction reactance and leakage reactance. Okay. Armature reaction reactance, you already know what is armature reaction reactance. That the reaction of the armature flux with the field flux. That is the represented by as the armature reaction reactance. Okay. So that basically is the mutual flux. That means mutual flux means flux linking the armature as well as field winding. Okay, but a part of the armature flux is not linking the field winding. Okay, why? Because that is the leakage flux. That's why the synchronous reactance basically will be a combination of the leakage reactance due to the leakage flux and the armature reaction reactance due to the armature reaction flux. Okay. And EF is the generated voltage, Vt is the terminal voltage. Here, EF and Vt, they are making an angle. That angle we have uh, indicated here by angle, this delta. Okay, this is the angle delta between induced EMF and the terminal voltage. Okay, and this is IA. IA is making a small angle with terminal voltage. It is lagging. Say if this angle is say theta, then this theta is the power factor angle. This has not been written here, so it may assume some angle here. That basically is the power factor angle of the generator. Okay. Now, is these things clear? What I have discussed so far? Any question here? Bolo. Are you having any question or it is clear? Any doubt, any question? Could you understand?
Yes, sir.
Okay.
Yes, sir.
Now, delta is the angle between induced EMF and terminal voltage. This delta is given different names. What are the names? Power angle. It is sometimes called power angle. It is sometimes called load angle. Also, it is called torque angle. Generally, in power system analysis, most of the cases we shall be using the term power angle. But in machine analysis, it is torque angle or sometimes it is load angle. Okay. So now you see EF is the induced voltage, Vt is the terminal voltage. Between EF and Vt, which phasor is lagging and which phasor is leading here? Can you tell me? Which phasor is leading and which phasor is lagging?
VT lagging, EF leading.
Which one?
VT, I think VT is lagging.
BT is lagging EF. Okay, BT is lagging EF.
Yes, yes.
Okay. Why BT is lagging EF? Because I were drawn like this. EF will be lagging phi f by 90 degree. So this is lagging direction with respect to this. So obviously this also is lagging direction with respect to T1. That means you see that generated voltage is leading the terminal voltage. What is the direction of power flow for a generator? Power is flowing from the generator to the power system. That is from the induced EMF to the terminal voltage. So direction of power flow is, we may say that it is from the leading vector to lagging vector. Okay, power always flows from a leading vector to lagging vector. We have seen this for generator, it is happening like this, but it is true always, or will always flow from a leading vector, in this case that is EF, to a lagging vector, in this case that is VT. Quite clear? So in generator, power is flowing from the inside of the machine to terminal voltage to external power system, or we can say it that from a leading vector EF to a lagging vector VT. This is the direction of power flow. Okay. Now, what is that power that will be flowing? Let us now try to derive the expression for that power. Okay. Before that, sorry, let us try to draw the from this phasor diagram. Let us draw the equivalent circuit first. How we draw the equivalent circuit? For that, let us concentrate on this part of the phasor diagram only, consisting of EF, VT, and IA. EF is the generated voltage. Let us show it here. This is the generated voltage. Then VT is the terminal voltage. So VT is the terminal voltage available here. In between, there is a voltage drop JIA XS that may be represented by the reactance here XS. When IA is flowing through XS, then drop is J times IA XS. Where from this J is coming? Because the reactance is basically J XS. We have not written J here, but basically it is J XS. So J times IA XS is the drop. So this is the generated voltage, this is the terminal voltage, this is the reactance of the machine, where when current flowing is IA, voltage drop is JIAX. So this gives you the equivalent circuit of the cylindrical rotor type synchronous generator. Okay. Now this voltage is the generated voltage, AC voltage, terminal voltage, this is the AC voltage. So between these two, let us assume that VT may be considered to be the reference phasor. So we consider VT to have an angle equal to 0 degree, means this is considered to be the reference phasor. So if this is the reference phasor, what will be the phase of EF? Phase of EF was delta, means that is positive delta. That means EF is leading VT by angle delta. Okay, so this is the equivalent circuit. Now from this equivalent circuit, let us find out the expression for current, IA. What is current? Current is EF at an angle of delta minus VT at an angle of 0 divided by J times XS. Divided by J XS is the current, armature current or current flowing from the machine to the power system. So if you know the expression for current, what is the power expression for power? P plus JQ. P plus JQ we may write at V into I conjugate. Already you know that V into I conjugate is the expression for power, complex power. If you consider power in the reactive power to be positive for inductive load, then P plus JQ is the expression for complex power, and that may be represented as VT terminal voltage into I conjugate. So if this is I conjugate, you write the expression for power here. It will be, obviously you see that we are measuring this power at the terminal of the generator. We are measuring it here. So it is VT multiplied by current conjugate. So how much power is being delivered by the generator to power system? That is what we are measuring. Okay. So it will be VT EF at an angle of minus delta. Why minus delta? Because I am making the conjugate of current. So when you take the conjugate of the current, then obviously angle here will be the, if it is a positive angle, it has to be made negative angle. If it is a negative angle, it has to be made positive. Okay. So EF at an angle of minus delta will be here. So EF Vt at an angle of minus delta minus Vt square, because this is zero, positive and negative, there is no change. So Vt square by Jxs. What is the conjugate of Jxs? It will be minus Jxs. So it is becoming minus Jxs because of we are taking conjugate of this current. So it is minus Jx. So from this, now we can actually separate the real and imaginary part, and real part may be equated with the active power P and written as EFBT by XS sin delta. Imaginary part may be equated with Q. So Q becomes equal to Vt by XS EF cosine delta minus Vt. So this expression I have actually written from here. Now you see whether you can actually link these equations with this equation here. Whether this is correctly written, could you understand this or not? Well, that P equal to here Bt by xs sin delta, it is taken. It is actually found from this expression P plus jq equal to Vt at an angle of minus delta minus Vt square by minus Jxs. From this expression, we have found P equal to EF Vt by Xs sin delta and Q equal to Vt by Xs EF cosine delta minus Vt. So can you understand these steps? How from here we have obtained P and we obtained Q here. Can you understand it, or it has to be further explained? Well, is it clear? Okay. So if you divide this expression into real and imaginary part, you will be having these two expressions. So P is EF Bt by xs sin delta, Q equal to Bt by xs EF cosine delta minus Bt. So we have developed power equation from the equivalent circuit of the machine. Equivalent circuit of the machine we have obtained from the Phasor diagram. Okay, and Phasor diagram we have obtained from the basic operating principle of synchronous generator. Now we shall be actually examining how we can vary P and we can vary Q. Why? Because we know that for frequency control and voltage control, P and Q are to be controlled respectively. For frequency control, you will be controlling P, active power generation. For voltage control, you have to control the Q, the reactive power generation. Okay, first of all, consider the active power. You see that if we keep the field current constant, then what will be the value of this EFVT by XS sin delta? So let us see uh, how we can explain this if we keep the field current constant. If the field current constant, then obviously EF will remain constant because generated voltage depends upon the field flux and the speed of operation of the machine. It is a synchronous machine, so obviously for synchronous machine, speed of rotation is constant. It has to rotate at synchronous speed. So generated voltage can be varied only by varying the field flux. Speed variation will not be effective because we are not allowed to vary speed because this is synchronous generator. So you can vary the generated voltage by varying the field flux only or by varying the field current only. If we are keeping the field current constant, then EF will also be constant. Okay, EF is also constant. So EF is constant. What will happen to VT? We are connecting our generator to infinite bus. So what is about VT? What is the nature of VT? Is it constant or is it
It's
variable
a
now?
constant.
constant, because we are connecting our generator to infinite bus with a
Yes.
constant voltage bus. So Vt is constant, EF is constant, because field current for the time being we are not varying. Excess is also constant. Why? Because excess is the synchronous reactance. How much is the synchronous reactance? This depends upon the design and you can say the fabrication of the machine. So once the machine is fabricated, okay, once you are using this machine, excess you can no longer change. It is also constant. That means EF, BT, and excess, all three are constant. Means this is having a constant value. Say this constant value we write as P maximum. Okay. Why we call this as P maximum? Because power will be maximum when this delta is 90 degree. Because what is the maximum value of sine delta? Maximum value is 1. And when the value is 1, when delta is 90 degree. So if delta assumes a value equal to 90 degree, then P will be maximum, and that becomes equal to EFBT by XS. So we shall henceforth refer this EFBT by XS as the Pmax. That means this is the maximum possible power that the machine can deliver, and that is EFBT by XS. Okay, that is P maximum. So the expression for the active power we may write as P equal to P maximum sine delta, where P maximum equal to EFBT by XS. Okay. Now you see that this is how we can write the power. That means you see the basically P equal to FBT by XS sine delta. If this is constant, then obviously you have the expression for power as a sinusoidal curve. Basically, you can say that P will follow a sinusoidal curve like this. P will follow a curve like this, sinusoidal curve. P equal to P maximum sine delta, EFBT by XS sine delta. So a sinusoidal curve will be followed. Okay. Now we shall be examining how this P may be varied. Okay, how this P may be varied. P is P maximum sine delta. So how P may be varied? Can you suggest? We want the variation of active power generation. So how can you achieve this? How can you do this?
In the sine delta.
Delta has to be varied. Okay. Delta has, so basically if P is represented as P maximum sine delta, and if we assume P maximum is constant, then that means EF BT by X is constant, then obviously the only possibility is to vary delta. So we shall basically be varying delta. But before going to that part, let us see what would have happened had we varied EF. If we vary EF, obviously then P maximum is not constant. It is somewhat different because EF becomes variable. Now, assuming that it is permissible to vary EF also. Later on, we shall see that we can vary EF also. For some other reason, we shall be varying EF. But if EF is permitted to be varied, then can we control the active power generation by varying the field current or varying EF? Or should we vary the active power by varying EF or by varying field current? If field current is constant, then maximum value of power is also constant. That means it will follow a definite power angle curve. This is called the power angle curve. This sinusoidal curve is called the power angle curve. But if EF is allowed to vary, obviously Pmax also will vary because EF also will be varying. If EF is allowed to vary, that means if field current is allowed to vary, shall we go for controlling the P active power by varying the field current of the generator? Shall we do this? বুঝতে পেরেছো? যদি ফিল্ড কারেন্টটা পারমিট করা হয় ভ্যারি করার জন্য, তাহলে কি ফিল্ড কারেন্ট ভ্যারি করে আমরা অ্যাক্টিভ পাওয়ারকে ভ্যারি করব বা অ্যাক্টিভ পাওয়ারকে ভ্যারি করতে পারবো? Is the question clear?
হ্যাঁ স্যার ভ্যারি করা যাবে।
ভ্যারি করা যাবে। কেন ভ্যারি করা যাবে? কারণ যদি ফিল্ড কারেন্ট ভ্যারি করে, ইএফ ভ্যারি করবে, and EF varies, then obviously P also varies. That is mathematically it is true, there is no problem in it, but will you be varying P by varying IF, varying field current? Will you be doing that? Or should it be done in power system? Will it be done at power system at all? আমরা কি এইটা ভেরি করে ফিল্ড কারেন্ট ভেরি করে অ্যাক্টিভ পাওয়ার কন্ট্রোল করব?
না স্যার।
কেন করব না?
স্যার ভিটাও চেঞ্জ হয়ে যাবে তাহলে।
হ্যাঁ,
ভিটা
না ভি চেঞ্জ হোক, কিছুটা ভি তো আমরা পরে দেখবো যে আমরা ভি কেও তো কন্ট্রোল করতে হবে, মানে ভি কে চেঞ্জও করতে হবে, মানে যেটাই তুমি কন্ট্রোল করো সেটা ভ্যারিয়েশন যদি পারমিট না করা যায় তাহলে তুমি কন্ট্রোলই বা করবে কি করে? সো সাম ভেরিয়েশন ইন ভি অলসো উইল বি permitted and it has to be done. Okay, but shall we vary field current in order to vary the active power generation? Will it be possible at all? If you simply look at the expression, then it is possible. Okay, because there is a dependence between P and EF. There is a dependence. P depends upon EF. So if we change EF, obviously P also will change. How will you will be changing EF? Obviously by changing the field current. So it means by varying field current, you can vary P. But practically, will it be done? সত্যি কি এরকম করা হবে? যদি করা হবে কেন করা হবে এটা? যদি না করা হয় কেন করা হবে না? Okay, we should know exactly why it is not permitted or why it has to be done. বলো কেউ?
Sir, I think
idea?
there should be a limit of changing the field current due to the insulation property, field current or field voltage. So we cannot change it. আমাদের মানে যতটা চাইবো ততটা চেঞ্জ করা মানে পারমিসিবল নাও হতে পারে।
নাও হতে পারে। Anybody else? আর কেউ কিছু
সার্কিটের
বলবে?
কারণে।
Any other answer from anybody of you? আর কারো কিছু মনে হচ্ছে? আচ্ছা, দেখো বেসিক্যালি how we will be changing IF? What should be the method to change IF? IF is an electrical quantity, right? So basically the current has to be changed. So how this IF has to be changed? We'll be supplying this IF basically, maybe it is a direct current, so maybe a DC generator will be supplying this current. Okay, so a DC generator output will be used to change the field current of the generator. So if you vary the power output of the generator, if you want to vary the power output of the generator by the varying the field current of the generator, then basically you have to vary the power output of the DC machine or DC generator that is driving current to the field winding of the generator. তাই তো? তার মানে কি একটা ডিসি জেনারেটরের একটা ইলেকট্রিক্যাল জেনারেটরের আউটপুট আমি ভেরি করছি কেন? ভেরি করছি টু চেঞ্জ দ্য পাওয়ার আউটপুট অফ দ্য এসি জেনারেটর। তাহলে এইভাবে যদি আমি একটা জেনারেটরের আউটপুট ভেরি করছি কেন? কারণ আরেকটা জেনারেটরের আউটপুট ভেরি করব। তাহলে ধরা যাক আমাকে পাওয়ার আউটপুট বাড়াতে হবে বাই 10 মেগাওয়াট। Then how shall I obtain this power output, 10 megawatt extra output from the generator? Yeah, if I want to change the output of the generator by changing the field current, then obviously 10 megawatt power has to be inserted into the generator. Then only you can extract 10 megawatt power from the generator. 10 megawatt power will be inserted into the generator through the field winding. Then through the armature winding, you will be extracting 10 megawatt power. Am I correct or not? বুঝতে পেরেছো? তুমি 10 megawatt power output বাড়াতে চাইছো, say by changing the field current of the generator. Then this 10 megawatt power must first be inserted into the generator. Then only you will be drawing that power, because generator basically is not a generator, it is a converter of power. তাই তো? তাহলে একটা ইলেকট্রিক্যাল পাওয়ার তুমি তাকে ইনপুট হিসেবে দিচ্ছ টু দ্য জেনারেটর থ্রু ফিল্ড ওয়াইন্ডিং। দ্যাট মিনস টু deliver 10 megawatt output, extra output from the generator, obviously you have to supply 10 megawatt power to the generator. Then only you can extract 10 megawatt from the generator. Otherwise you cannot extract. Where from it will give power? Generator cannot generate, it can convert only. তাহলে তুমি কি করছো, একটা জেসি জেনারেটর থেকে 10 মেগাওয়াট পাওয়ার 10 মেগাওয়াট পাওয়ার you are delivering to AC generator, and from AC generator you are extracting then that 10 megawatt. Is not it? Is it correct?
Yes.
Huh?
Yes.
Yes. Then should you do this? Because in that case you could directly take 10 megawatt output from the AC generator. Why the AC generator is in between? Because efficiency of no generator can be 100%. কিছুটা তো লস হবে, আমি সেই লসের মধ্যে যাবই বা কেন? আর আমি যদি 10 মেগাওয়াট পাওয়ার আমি ডিসি জেনারেটর দিয়ে এসি জেনারেটরে ইনসার্ট করি, why not I am taking that power directly to the power system? Okay, so there is no, you can say that the meaning of that step. If you vary the power output of the generator by varying the field current, it will be much better to draw that power directly from the DC generator who is supplying power to the AC generator. So that step is not recommended. Rather, it will leave this type of useless job nobody will do. এটা তো একটা unnecessary একটা স্টেপ মাঝখানে থাকা হবে, তাহলে এটা দরকার নেই, এটা করা হবে না। Basic purpose of the field winding is to generate the magnetic field. ওকে, পাওয়ার আমি চেঞ্জ করব অন্যভাবে, আমি পাওয়ারটা সাপ্লাই দেব অন্যভাবে। এবার the basic role of supplying field current to the generator is to generate the magnetic field. So I cannot supply field current to draw extra power from the machine. At least কখনো কখনো সেটা অন্য পারপাসে করা হতে পারে, not for this purpose, not for drawing power. Okay, so therefore you see that active power control of the generator cannot be done by varying the field current, or should not be done by varying the field current. Rather, it has to be done, it should be done by using the other option. What is the other option? Other option is to vary the delta, is to vary delta. Okay, so this is P maximum sine delta, and you have to vary the delta. Now we should have to see how delta can be varied. Am I clear? বুঝতে পেরেছো যে delta vary করেই power outputটা vary করতে হবে? Is it clear?
Yes.
Okay, you cannot change field current to change the power output. Field current তুমি change করবে, but for some other purpose. So what is that purpose? We shall explain later on. But field current will not be controlled for controlling the active power output of the generator, because in that case we shall have to supply a huge field current to the generator, which is not possible. Okay, and obviously I cannot change active power input to the generator to change the active power output from the generator. That means a redundant step, an unwanted step is inserted in this process that is not needed. Rather, directly I shall take 10 megawatt power output from the this generator itself. That's why the only method of changing the active power output of the generator, or changing the active power output, is to change the delta. Now, how delta can be changed? What is delta? You see, delta basically is the angle between the induced EMF and terminal voltage. Okay, delta is the angle between the induced EMF and the terminal voltage. So what is the speed of rotation of the EF vector? What is the speed of rotation of the EF vector?
Synchronous speed.
Synchronous. Why it is synchronous?
Because field, it is related to the field winding. So field winding is rotating at synchronous speed.
Yeah. And because also it is along the quadrature axis of the rotor. So it will always lie on the quadrature axis of the rotor. See, that since the rotor is rotating at synchronous speed, quadrature axis also will be rotating at synchronous speed. And that is the speed of the vector EF. So EF is rotating at a speed equal to synchronous. What is the frequency of the vector Vt, or what is the speed of rotation of the vector Vt? It is the
It is synchronous.
terminal voltage. It is the then
Synchronous.
it is also the synchronous speed.
Yes,
Am I
sir.
clear? It is the synchronous speed. Okay, now since this is rotor is rotating at synchronous speed, and this is also rotating at synchronous speed. Why it is rotating at synchronous speed? Where the VT is connected? Terminal of the generator is connected to the power system. Okay. What is the frequency of the power system? Voltage. What is the frequency of the power system? Is the synchronous frequency. And because power system is connected at, or the generator is connected at infinite bus, and that infinite bus is having a frequency equal to synchronous frequency. Am I clear? So BT will be rotating at synchronous speed because generator terminal is connected to the infinite bus, and infinite bus is having a frequency equal to synchronous frequency, which is constant frequency, because the infinite bus is having a constant frequency. So there the frequency is constant, and that frequency is nothing but the synchronous frequency. আর আমরা বলতে পারি VT is always having a frequency or a speed equal to synchronous frequency. Frequency মানে synchronous যদি হয়, what is the angular speed? That is also omega 2 pi fs is the angular speed. Okay, so it is at synchronous speed it is rotating, and EF is rotating along with the rotor of the generator. তাহলে আমি যদি ডেল্টাকে ভ্যারি করতে চাই, কিভাবে সেটা সম্ভব? How that is possible? Because now you see that it is rotating at synchronous frequency because it is connected, generator is connected to the infinite bus. Infinite bus is having a frequency equal to the synchronous frequency, a constant frequency. So BT is having a constant frequency, or angular speed of BT is synchronous speed omega s corresponding to 2 pi into fs. Fs is the synchronous speed of the infinite bus. And what is the speed of the rotor? Say rotor speed is omega r, ধরা যাক omega r is the rotor angular speed, and that is also equal to synchronous because rotor is rotating at synchronous speed. বুঝতে পেরেছো? এবার rotor synchronous speed, but will the rotor of the synchronous machine always rotate at synchronous speed? সব সময় কি rotor synchronous speed এ ঘুরবে? বা সব সময় কি synchronous speed এ ঘুরতে পারবে? Could you get my question? Could you understand my question? Is it possible for the rotor of a synchronous machine to rotate always at synchronous speed?
স্যার স্টিম ইনপুটের যদি চেঞ্জ হয় বা স্টিম ইনপুটে যদি কিছু হয় তাহলে চেঞ্জ হলে
ইনপুটে কিছু হলে হবে, যদি লোড চেঞ্জ হয় তাহলেও হবে, কারণ আমরা আগে প্রথমে যখন ফ্রিকোয়েন্সি চেঞ্জ দেখেছিলাম কেন হচ্ছে, because speed of the generator is changing. Okay, when suddenly a load is connected, the speed of the generator is changing, that's why the frequency is changing. তাই তো, কাজে সাডেনলি যদি আমি রোটর, অর্থাৎ কি রোটর যে সবসময় সিঙ্ক্রোনাস স্পিডে ঘুরবে, দ্যাট ইজ নট দ্য সিচুয়েশন. রোটর মে রোটেট at any speed but at steady state, but when the power system is operating at steady state, or when the power system is at its normal operating condition, then the rotor speed will be synchronous speed. Am I clear? অর্থাৎ রোটর স্পিড সিঙ্ক্রোনাস ছাড়া অন্য কোনো স্পিডে হতে পারে, কোনো সময় বেড়ে যেতে পারে, কোনো সময় কমে যেতে পারে। Sometimes it may be greater than synchronous, sometimes it may be less than synchronous. But when the machine becomes stable, then its speed must be corresponding to the synchronous speed. অর্থাৎ steady state condition এ this angle delta must be constant. তাহলে যেহেতু synchronous speed ছাড়া অন্য স্পিডেও ঘুরতে পারে মেশিন, তাহলে how actually delta may be changed? You see that delta may be changed if suddenly you actually give more power input to the turbine. আমি টারবাইনে সাডেনলি আমি টারবাইন ভালভটা একটু বেশি করে খুলে দিলাম, তাহলে কি হবে? দেন more steam will be entering into the turbine. ওকে, টারবাইন আমি যদি টারবাইন ভালভটা একটু বেশি করে খুলে দিই, স্টিম ভালভটা বেশি ওপেনিংটা বাড়িয়ে দিই, তাহলে কি হবে? Steam flow rate will increase. As the steam flow rate is increasing means, if the steam flow rate increases means the more power is entering into the machine বলা যেতে পারে. As a result, what will happen? Generator will attempt to rotate at a higher speed, and since it is attempting to rotate at a higher speed, what will happen to delta? It is rotating at synchronous speed. BT is rotating at synchronous speed. If EF rotates at a higher speed, then it is moving in this direction. Okay, then delta will be increasing. তার মানে if I want to vary delta, what should be the method? The method has to be change the steam flow rate. Okay, I have to change the steam flow rate, then delta will be changed. Am I clear? বুঝতে পেরেছো?
Sir, but sir, if we change the EF, then EF will change to high axis. It's not then constant. It's also changed. This vector also change.
কোনটা কোনটা বলো?
Sir, VT plus IA axis EF হচ্ছে, তাহলে EF টা যদি বাড়ে বা কমে, তাহলে VT এর সঙ্গে I axis ভেক্টরটা তো স্যার
পরে আসছি। ওকে, EF চেঞ্জ করলে প্রথম কথা আমি এখানে কি বললাম যে আমি EF চেঞ্জ করে কেন অ্যাক্টিভ পাওয়ার চেঞ্জ করব না, সেটা পরে বোঝা যায়। ইজ দ্যাট ক্লিয়ার?
ইয়েস।
তাহলে EF চেঞ্জ করলে এফেক্টটা কি হবে, কোন সময় EF চেঞ্জ করব সেটা আমি পরে দেখব, এবং তখন দেখব what will be the impact of variation of EF. That obviously we shall examine. Okay, কিন্তু সেটা পরে। For the time being, perhaps now, my question is it clear to you why we should not change EF to very active power? EF আমি চেঞ্জ করতে পারি, but we should not do that to very active power, because in that case I am changing active power to get more active power. That should not be the method of operation. Okay, that is what I am trying to make you understand. Okay, এবার তাহলে অল্টারনেটিভটা হচ্ছে to change delta. Now the question is how delta can be changed. Obviously, how can be delta can be changed by temporarily creating a speed variation of the rotor. Right? Because BD is rotating at synchronous speed, EF is along the rotating with the rotor. So if the rotor is rotating at synchronous speed, then EF is also rotating at synchronous speed. In that case, delta will have a constant value, fixed value. But somehow we can make an attempt to vary the speed of the machine. যেভাবেই পারি আমি স্পিডের যদি ভ্যারিয়েশন করতে পারি, তাহলে কি হবে? তাহলে delta will vary, because in that case speed of VT and speed of EF, there will be difference between these two. So if I can rotate the generator rotor at a slightly higher speed than synchronous speed, then what will happen? Then delta will increase, and if delta increases, তাহলে কি হবে? তাহলে দেখো তুমি, if somehow delta increases, then obviously from this curve you see, if delta increases, then you say larger value of delta means operating. If this peak of this power angle curve is fixed, why it will be fixed? Because I have not changed the value of EF, I have not changed the value of BT. So if power angle, if the value of delta is changed, so obviously power output P also will be changed. Okay, from here, say it is here, so power output P will be changing. Therefore, you see that varying active power output of the generator will be possible if somehow you can make a variation in the power angle of the generator. And how power angle may be varied? By attempting to increase the speed of the generator momentarily. আমি রোটরকে কোনো একটা ভাবে একটু হায়ার স্পিডে ঘোরানোর চেষ্টা করলাম, রোটর যে একটু হায়ার স্পিডে ঘুরতে শুরু করলো, দেন a larger value of delta will be automatically achieved. Can automatically achieved because in that case EF is rotating at a higher speed with respect to VT, delta will increase. Okay, এইবার কথা হচ্ছে তাহলে how we can make this attempt, how we can try to rotate the generator at a higher speed. কি করতে পারি? তাহলে আমি কি করব, আমি একটু বেশি স্টিম পাঠিয়ে দেবো টারবাইনে, একটু বেশি স্টিম ফ্লো রেটটা বাড়িয়ে দেবো। কি করে বাড়াবো? অবভিয়াসলি বাই ইনক্রিজিং দ্য ওপেনিং অফ দ্য স্টিম ভালভ। এবার বেশি স্টিম টারবাইনে গিয়ে পৌঁছাচ্ছে মানে there is more capability of that steam, অর্থাৎ বেশি ওয়ার্ক করার যে একটা ক্যাপাবিলিটি, that is being inserted into the machine. That means power input to the machine is increased. As power input to the machine has been increased, obviously power output of the machine also will increase, and that is reflected by the variation of delta. সেই জন্য ডেল্টা যখন বাড়ছে আমি বেশি কয়েকটি পাওয়ার আউটপুট পাচ্ছি মেশিন থেকে, বিকজ I have given more power input to the generator. Is it clear? বুঝতে পেরেছো?
Yes, sir.
Yes, sir.
Okay, so this is how you can change the delta. অর্থাৎ to change the active power output, what you have to do? You have to vary delta. And how delta can be changed? By turbine output, by varying the turbine output of the generator. And this turbine output power may be varied by varying the input to the turbine. Turbine input comes from the, for a steam turbine input is from boiler. So who is responsible for that? Obviously the turbine valve is responsible for that. That means you have to adjust the opening of the turbine valve. If you want to increase the power, open the turbine valve a little bit. If you want to decrease the power output, reduce the opening of the turbine valve or steam valve a little bit. This has to be done. Okay, so this is how P has to be varied. Okay, now other aspects are there, we shall be discussing that how much we can vary P. So those things we shall be discussing, and then we shall see how Q may be varied. So these discussions, remaining discussion, obviously we shall be doing in our next class on Tuesday at 11 o'clock. Okay, from therefore Tuesday it will be 11 to 12:30. Okay, are you having any more question here? If you are having any question, then you can ask me. Otherwise, we shall be proceeding to conclude our session today.